Now, discussions on system engineering become very complicated due to the very broad mandate of the discipline, the wide range of the types of systems involved, the complexity and interrelationship of many engineering activities, and the relationships with other disciplines throughout the entire system lifecycle, not to mention the experience and the backgrounds of the people having the discussion. The ability to understand a complex subject such as system engineering is greatly enhanced by a solid framework within which concepts can be considered. There are a number of excellent system engineering standards available today that contribute to the elements of a suitable framework, but each standard contains complexity, terminology and detail that itself requires interpretation. The entry level for many students, for junior engineers and for project managers, therefore doesn't allow the use of such standards as effective frameworks to examine systems engineering. For the remainder of this course, we use the simple framework which shows three main elements of systems engineering: processes, that is the doing element; management, the controlling element; and tools, which support both management and processes. These elements are placed within the context of a fourth element called related disciplines. System engineering processes and tasks are divided into the life cycle stages within which they typically occur. In this course, we don't attempt to detail exhaustively all system engineering processes. Instead, we concentrate on the intent and the main aim of each phase within the system lifecycle and examine some of the likely techniques that may be used to arrive at that aim. We place particular emphasis on the acquisition phase of the lifecycle, as it is the phase during which system engineering has the ability to have the most impact on the system. Systems engineering management is an overarching activity responsible for directing the systems engineering effort, monitoring and reporting that effort to the appropriate areas, and reviewing and auditing the effort at critical stages in the entire process. Later in the course, we address briefly the major system engineering management elements of technical reviews and audits, system test and evaluation, technical risk management, configuration management, the use of specifications and standards, integration management, and system engineering management planning. The preeminent position of system engineering management in our framework illustrates that it's the key to the entire system engineering effort. Now, many tools exist to assist system engineering processes and management. These tools range from techniques and methods through to system engineering standards. Here we describe the most popular tools and standards without repeating information that might be contained elsewhere. Throughout the course, we present generic process tools, such as the requirements breakdown structure, the RBS, functional flow block diagrams, FFBDs, work breakdown structures, WBS, trade-off analyses, and prototyping and simulation as examples of tools that may be applied to the system engineering effort for processes. We also describe the systems engineering management tools of standards and capability maturity models. Now, there are many disciplines, both technical and non-technical, related to systems engineering, such as project management, logistics management, quality assurance, requirements engineering, hardware engineering, software engineering, and so on. The relationship between the related disciplines and the other facets of systems engineering depends very much on the discipline in question. Some, such as project management, oversee the whole system engineering discipline, while others, such as hardware and software engineering, sit between systems engineering management and the processes, and others, such as quality assurance, sit alongside the system engineering effort. We discuss these disciplines and their relation to system engineering at the end of the course. All extant system engineering standards and practices extol processes that were built around an iterative application of analysis, synthesis, and evaluation. The iterative nature of the application is critical to system engineering processes. Initially, the analysis, synthesis, evaluation loop is applied at the system level, and then reapplied at the subsystem level, then the assembly level, and so on until the entire process is complete. During the early stages, the customer is heavily involved. Towards the end, the contractor is mainly responsible, monitored by the customer. Prior to detailing the individual activities within the system engineering processes, it's worth considering for a brief moment the basic foundations that the analysis, synthesis, evaluation loop provides. The concept's not complex, it's simply a good, sound approach to problem solving that's applicable in any domain, but particularly fundamental to systems engineering. During conceptual design, analysis investigates the business and stakeholder needs and identifies the essential requirements of the system in order to meet those needs. Analysis at the system level aims to answer the what, how well and why questions that are relative to system design. Analysis activities continue then throughout the subsequent life cycle to help in defining the low-level requirements associated with the physical aspects, the hows, of the system. Now, depending on the particular design phase, these requirements may be grouped in accordance with some logical criteria that makes them easier to manage, and then allocated to a particular physical component. That is, the component becomes responsible for satisfying those functions that have been allocated to it. The allocation of requirements forms a description of the system elements and therefore assists in the process of synthesis or design, that is, answering the how questions. So once the analysis activity resolves what is required, as well as how well and why, synthesis, or design, then determines the how. Synthesis is the process where creativity and technology are combined to produce a design that best meets the stated system requirements. The term synthesis is more appropriate than design in the system engineering context because it hints at the evolutionary nature of the design and development. So analysis has told us what the system will do and how well it will do it. Synthesis proposes how to achieve this. And synthesis, of course, is probably the most widely recognised role of a professional engineer. In the early system engineering process, synthesis is limited to defining the logical design of the system and then considering all of the technical approaches. From this consideration, the best approach is selected and the process then moves to the next level of detail. Later in the system engineering processes, the selected design concept is synthesised further until the complete design is finalised. So after we've completed analysis and then synthesis, we have some candidate designs. Evaluation is the process of investigating the trade-offs then between those designs. At the earliest time, it's the evaluation between requirements and design alternatives and making the necessary decisions. But that process continues throughout all stages of the system engineering effort, ultimately determining whether the system satisfies the original requirements. So trade-off analysis is one of the tools available to the system designer in performing evaluation of competing requirements or designs. We discuss trade-off analysis in more detail later. The outcome of the evaluation is a selection or confirmation of the desired approach to the design. Discrepancies are also identified if they're applicable and may result in further analysis and synthesis as the analysis, synthesis, evaluation loop is closed. So you've shown how the analysis, synthesis, evaluation loop can be applied across all the activities in the life cycle. This figure summarises that by showing you in a visual way how it can be applied iteratively to each of those activities. So that finishes the introductory presentations for Module 2. In the next module, we begin our more detailed discussion of system engineering processes by examining the role of requirements engineering and the major artefacts that are produced as the system is developed. If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.